Thank you. Hello, everybody. My name is Stephan. I'm going to talk about Apache Flink today. I've actually been here a year ago talking about a project called Stratosphere. That was back then a project coming out of university research, collaborative research here in the area of Berlin. And it was just very recently, last year, that it had been accepted at the Apache Incubator as a project. It was, sorry, I just hit a button here. Yeah, it was that it had been accepted as an Apache project into the incubator. It was still called Stratosphere back then. I think we knew that we were renaming it to Flink. So now a year later, I'm actually here to sort of show you what this has become, what actually Flink has become within a year. A little about myself, maybe. I think the bio in the program is wrong. We just accidentally forward copied the one from last year. So the core team behind Flink that started this effort, giving it to the Apache Incubator and so on, is no longer with the university, even though it says it in the program. A bunch of us actually started a company here in Berlin called Data Artisans, and we're developing Flink. We're supporting people who want to use it. Okay, let me try and calibrate a little bit to how much you may have heard or may have not heard about Flink before. So can I briefly ask you, who of you has actually heard of Flink before this talk? Oh, that's a good bunch. Who of you has actually tried it out in terms of downloaded it and tried to write a few jobs? That's actually a few hands at least. That's actually cool to see. Okay. To get a little bit the notion, who of you is familiar with Storm, Spark? All right, I don't ask about MapReduce. I assume that this is. I see a lot of hands there. Okay, that's actually good. So let me try and use this to put things into perspective a little bit. Okay, so what you can see here is that since the last time we were here at Berlin Buzzwords, we started out with a system called Stratosphere. It was a pretty small thing. It had a bit of a runtime core, a batch API, and a few modes to run your jobs. And within this 1 year, actually, the Flink community has grown this to quite a fat stack, which can do a few very interesting things. And I'd like to introduce you to those in this talk. So first of all, in the heart, what is Flink? Flink is it's an entire like software stack, but the very heart of Flink is a streaming data flow engine, an engine that thinks of programs in terms of operators and data streams that connect them. It is in some sense like a Storm topology, only that these operators may be extremely rich, and that the way of communication and thinking about state and snapshotting and so on works differently. But yeah, I mean the notion of having a data flow is a bit like a streaming topology. This streaming data flow engine can present itself actually as a batch processor and as a stream processor, both at the same time. And I mean, it seems natural that a streaming data flow can present itself as a stream processor, as a batch processor. I'm going to talk a little bit about those details later. A streaming engine turns out to be actually quite a good fit for a batch processor. And while this may initially sound a little esoteric for those of you that have read a little bit into, let's say, the blog posts from Martin Kleppmann or Jay Krabs, they might be familiar with the term kappa architecture, which is exactly that concept, running batch programs as special cases of streaming programs. So this is sort of what the concept that Flink follows here as well. I'll share a few details in a bit. So on top of these APIs, the batch API, we call that the data set API, thinking of a set as a fixed size data set distributed. The data stream API, thinking of data streams as infinite streams of data. On top of this data set, the batch API, we've added a couple of libraries. So there's support to run Hadoop, your Hadoop functions, map functions, reduce functions, input formats, output formats. There's something called the table API, which is a way of exposing these data sets in a more logical way. So not with a physical schema in the sense of there's a class or a tuple or so in Java or Scala that defines what this is, but something like a SQL schema that defines the data that goes to there. A graph API called Jelly, a machine learning library called, we haven't come up with a very good name right now, it's just called ML at this point in time. We're still open to good suggestions there. And there's quite a bit of work in progress. So there's an adapter to run Google Cloud Dataflow on Flink. It's Google's hosted service. So if you want to run it, on your own data infrastructure, you need another runner, and Flink is one of the candidates there. MRQL is another Apache project for I think a very, very principled functional API based on list comprehensions, and cascading. I would assume a lot of you have probably heard of cascading. It was one of the first tools on top of MapReduce to build more elaborate programs. So there's also work on running cascading on top of Flink. On the side of data streams, we have, interestingly, even though the runtime is streaming, we've spent initially a lot of work on the batch side because that seemed to be what people were familiar with, what they were using, they were looking at. We've recently started exposing the streaming capabilities of Flink a lot more with this data stream API, and started putting a few libraries on top of that as well. So this table API is in, I'd say, in a restricted form, also running on the data stream abstraction. Samoa is a very recent project that entered Apache, but it's very, very interesting. It's actually a machine learning library on top of streaming. So it's it thinks in terms of streams with asynchronous feedback and tries to do online learners based on these streams. And yeah, Cloud Dataflow also has a streaming component, and we're porting this actually to the data stream API as well. So with these abstractions sitting on top of the Flink stack, there's a couple of ways to run this in your infrastructure. So you can always run it locally in your IDE for debugging. You can run it what we call remote, we should probably call this bare metal or so. It is if you just run the Flink daemon on every machine, you can run it there. You can run it through Yarn. You can run it just embedded in other Java applications where it uses a very, very lightweight, non-parallel way of executing programs. And what is very interesting is that actually Tez is on this slide here. Apache Tez is a project that started out as part of the initiative to make Hive faster. I think it's mainly used actually as the distributed scheduling and communication backend of the newer versions of Hive on Tez. And the architecture of Flink is layered in such a way that we can swap a lot of components at individual parts. So we can actually say that we execute a streaming data flow if these streams happen to be file streams or so. So they're actually not infinite streams, but finite streams. They happen to represent batch programs. We can actually run those on this Tez engine, which is it's pretty good for a few use cases because it implements some very, very neat characteristics with Yarn, elasticity, and auto-scaling, and so on. Okay, but this talks about the core of Flink. So in order to understand why we push the design and the architecture of Flink the way it is, we should have a look at what were actually the use cases that we were trying to solve with Flink. And the set of use cases has become extremely diverse in that field. So we're definitely not looking at any use cases from the area of, let's say, more transactional processing, the field where you would use NoSQL style databases, HBase, MongoDB, Cassandra. So no, Flink is purely in the analytical side, but the analytical side in itself has become very, very diverse. And here are four use cases that I think sort of categorize a pretty broad spectrum of things that we were trying to do. Trying to run streaming topologies, real-time streaming topologies with complex operations and low latency complex operations in terms of being able to flexibly window the event streams and detect patterns on the event streams. At the same time, yeah, of course, batch pipelines are probably the most established use case of those. Large-scale machine learning is becoming increasingly interesting, and people are still showing quite an interest in graph analysis as well. So we're trying to look, okay, how can you build an engine that is a good match for these diverse use cases, in the terms of that the engine really has primitives to execute the operations that are needed for these use cases natively in the sense of that we don't try to work around certain characteristics and build things around that sort of mitigate these effects, but have proper primitives in there. So in order to make this a bit more concrete, what does a native support mean? I have two examples of what is not native. This may actually help to explain it. So if you look at machine learning in this field, one of the first things that people did was, MapReduce came out. It was great in the way it gave you a very nice and easy way of scaling computation. And in order to run to do the patterns that a lot of the machine learning algorithms have, the iterative computations, where you repeatedly loop over the training data in order to refine the parameters. The way people were implementing this is they were saying, okay, let me write one step as a MapReduce program and then repeatedly execute this. So in some sense, you were just running multiple jobs one after another. And it's very interesting. In some sense, this space is, to a large extent, still at this model, I think. I mean, people have come up with better things in terms of caching invariant stuff in memory, representing data structures in a way that can be reused across steps, but for a lot of systems, that's still pretty much what they're doing. And another use case is if you want to do streaming and what you have is a batch processor, you can do a lot of very small batch jobs, right? You can discretize the stream. You can chunk it up into little parts, and then run a batch part for each of those. And how large these parts are sort of depends on what you want to do, right? They can be daily. They can be second. This does work for a good set of use cases. It does put restrictions on what you can do across these batches, these discretized units. So whenever you have something that's not an easy aggregation that you carry across this may be a bit tricky to work with. So what we're looking at, what is a good abstraction actually to work with these use cases, and that sort of gave us the corner points for the design of Flink. And while those are not all of them, I think those are all the four most important ones that have sort of surfaced over the last year. And number one is, I've already hinted at that at the beginning, is, well, actually execute things as streams. The batch paradigm made a very strong move into this field with MapReduce, but we're actually seeing that the streaming paradigm is sort of coming back, because done the right way, it has a few interesting advantages over the batch paradigm, and interestingly, it subsumes it, because you can always think of batch as a special case of streaming. The second corner point is, if you want to do iterative computation, it's actually a good thing to sort of have this in the system, in the runtime, in the data flow, allow for a certain controlled way of feeding back data. Because if you're doing this, if you're actually making the system aware of these iterations, it can do a few nice things, and it's also not bound to certain barriers, so, as you are if you execute things in super steps, in synchronous super steps, in the bulk synchronous parallelism paradigm. The third point, and this is probably more interesting for streaming, but we see it also for graph analysis, is to really think about what to do with state during computation. The paradigm of the batch processing has been pretty much, you have an input, you have an output, the function produces its output based on the input. There's no state they concern themselves with. This is good for a lot of cases. Statelessness makes things extremely easy to reason about, easy to parallelize, and so on. For certain operations, having a way of having state is extremely beneficial, and there are ways of actually abstracting state such that it doesn't break that paradigm. In some cases it does, in some cases you also have to worry then exactly how does this affect my fault tolerance? And I'm going to talk about that in a bit. And the fourth point is something that has come up also in the last years more and more. It seems the Java ecosystem is really dominating this field, at least in the open source space, with a few exceptions. And if you want to do something data intensive, just relying on the garbage collector to handle all the data is not always working out the way you would want it to work out. So at some point you have to start worrying about how to use memory if you're going data intensive. And you can do this in the JVM. More and more projects are doing this. It's in the very core of Flink. I think the Spark project is starting to pick this up as well. Projects in C++ like Impala are doing it anyways because you have to. I think Drill is doing this quite in a quite sophisticated way. So yeah, it's one of our counterpoints as well. Okay, I've shown you the stack a little bit before. You remember the libraries on top, the batch and the streaming API, and then the runtime. If you write a program against such a system, what does it look like? How does the execution, the life cycle of such a program behave? So here's an example of such a program. It's a toy program. It's a very naive way of computing transitive closure, but yeah, just for the sake of example. What Flink does to every program is it transforms it into a parallel data flow. It does that in a phase that we call pre-flight, which runs on the Flink client side. So you're running a set of server processes in your cluster, a master process, worker processes, and there's a client process when you give your program to Flink. So what it is, it takes this Java or Scala program, and it goes through it. It builds a data flow graph, and it sends it through these two components: type extraction and optimizer. Type extraction is just a way to say, okay, we want to know at every function exactly what is the data types that go in and out, because we can use that to generate schema, to generate serializers and comparators, to do some checking. That, you know, if you happen to manage to use some casts and cheat around the type inference of the compiler to figure out that this doesn't crash at runtime, and also if we can pre-generate these serializers, we can do our managed memory operations much better. A bit more about this in a few minutes. Another part that's I think fairly interesting is the optimizer that we added to the system, which looks at these programs and determines a few things for you, like join algorithms, where to cache data in a loop invariant way. The result of all that is this streaming data flow, which is then given to the master, and the master starts deploying these operators into the cluster. They make handshakes on the streams that they produce and consume, and the master checks, the data flow topology and the metadata. So let me talk to you about the remainder. This is very high level, very coarse-grained. The remainder based on use case by use case. So the first use case I would like to talk about is data streaming analysis, because that, if you start out with a streaming engine, that's sort of where it naturally comes. And to give a bit of a context and how we see this field and where we see where Flink fits in, I've come to think of streaming infrastructure is in the way that companies use it. They usually have these three parts. They have a part that gathers data, that produces the initial streams. These are adapters to database logs, to sensors, to server logs, and so on. And then there's a second component. It's often called the broker, where I think Apache Kafka is sort of becoming the technology of choice in this area. It's a combination of it's a message queue / log that that is just a very good system for gathering data, buffering it, making it available for multiple consumers in a reliable way. And then there's the third part, which is taking these streams, consuming them, and enriching them, computing things over these streams, and this may naturally feed back into the broker and be available for other consumption. So for streaming, let me actually skip this slide and do it figure by figure. One of the core parts of Flink is that really everything is executed in a streaming way. So whenever you have a shuffle or an all-to-all connection between operators in the graph, shuffles and broadcasts, the data communication can actually be streamed. It is in many cases. So that means that when elements come in here, they pass through one operator, pass through the next. Let's say this computes a hash code to determine to which target to send it, and it sends it over to this machine. There's no synchronization boundaries where this really has to stop. There's a bit of buffering with an upper latency bound. If the buffers are not full by that time, they're going to get flushed. And in order to guarantee that we do not infinitely keep data and hold it back. So that is one thing. This is you find the same thing in Storm, I would say, or in Samza where the connections are implemented as Kafka queues. That makes sense if you want to go for low latency. And another thing is that we spent a lot of time, and we're still spending a lot of time in trying to see what are the APIs that you need to flexibly define the streaming workflows. And the current state that we have in the data stream API on Flink is like you can see here. This is the word count example. I apologize for that. You've probably seen it a million times. There's a slight variation of it, so this is why I dare to show it to you again. Here's the batch variant, the data set variant. Here's the data stream variant. It has slight differences, and it has this notion of defining windows of a certain length and a certain trigger interval. This is just an example here. So windowing in Flink in the current windowing implementation are defined exactly like this. You define how long are elements staying in windows and how often are these windows evaluated. So with these two policies, you can sort of quite flexibly define what you can do. You can use counts, you can use time, you can use some user-defined characteristics. Although as the more intransparent it gets to the system, it becomes a little trickier to define. But in general, the syntax is a bit like that. So we try to follow this fluent functional batch syntax, and the windowing mechanism, the way it's still under heavy evolution right now, but it has evolved into something that's quite interesting and flexible. So an interesting example that one of the committers likes to give is you can actually use this windowing system to define an analysis where you say, if I have a trace of GPS coordinates, I can use this to say every time this thing moved more than a mile, give me the average speed over the last 5 minutes or so. So this is possible with that. Okay. This is just a follow-up. Here's a little longer code excerpt from an example that implements a pipeline of processing of stock prices, and is actually monitoring for price variations of more than 5%. And you can basically see how it works. I mean, these APIs are, I think, what people nowadays are used to, and we try to follow this familiar pattern on the streaming side. Again, you can see the window definitions here, operations like mapping over a window. You can group by field names of the case classes and so on. So this should give you a pretty high level and way of doing things. Something that we're actually kind of proud of, the way we figured out how to do this, is how we do the fault tolerance and the checkpointing, because we were aiming for guarantees, for exactly once guarantees in such a system without the necessity to chop the stream up into mini batches. And the way that we that we realized this in the end was actually implementing a variant of the Chandy-Lampert algorithm on top of the streaming system. It's not important that you're familiar with this algorithm. It's actually a fairly old algorithm, like a lot of the fundamental algorithms in this field, getting a bit of a renaissance right now. With systems also like distributed graph lab, building on top of that, and so on. And the basic idea of this algorithm on top of the streaming topology is the following. We have data streams here, and periodically we start pushing so-called barriers through these streams. And these barriers logically chop the stream into different generations, a pre-checkpoint and a post-checkpoint generation. And this barrier it slides through the streaming topology. It can slide through each stream at its own speed. When it flushes the stream and pushes elements before it, and whenever it reaches an operator, it triggers a checkpoint of the state in that operator. That checkpoint can actually be written asynchronously. As soon as the writing starts, the barrier can leave that operator and flow on. And as soon as they have reached the end, and the sources acknowledge that they've received all of these barriers that slide through, and all operators acknowledge that they're done with their checkpoint, you know that actually this part is persistent. And the interesting thing is, while these barriers are sliding through, the operations can actually continue working. So you start emitting this, and you start pushing it through, and data immediately comes after that. It requires a little bit of finesse how you do the state handling and make sure that while you're writing, you're not overriding what you're doing in your data structures. But these are things you can, these are things where data structures exist that figure this out. So this is a very, it can give you it can give you the benefit of mini batching in terms of exactly once without interrupting the streams. This is basically what comes out of that. Okay, so much about streaming. I have a few minutes. That's good. So I can talk about batch pipelines. So when we talk about batch pipelines, this is just one example. It's a visualization from a batch program. Since Flink thinks of everything in dataflows, it's sort of a natural thing to just render these dataflows as such graphs. This is using the D3 library and a little JavaScript to take a Flink program and render it as a graph. So these things here are data sources. These are functions like map or reduce. There are binary functions like joins, unions, and so on. And this program, for example, I think it computes candidate flights based on schedules from various airlines. If you run this on top of Flink, and I said it's a streaming data flow, is there anything you have to look out for if you execute batch programs on a streaming data flow engine? What does that actually mean, executing batch flows on a streaming data flow? So there are a few dualities between batch processing and stream processing, where you can actually view batch processing as a special case of stream processing. So if we think of streaming programs as processing infinite streams, then a batch program is a program that runs over a finite stream. And this is actually not very surprising, right? I mean, every time you write a MapReduce program and you read a file from HDFS, you actually don't get the file as a batch copy into memory, right? You get a file stream. So in some sense, right, running a batch program as a streaming program is just following this paradigm conclusively to the end. In streaming programs, you can, whenever you do grouping, you can never group the entire stream because it's never going to end. There's never a point when you say, okay, I have all elements for this group, I can now do whatever aggregation or reduce function I want to run over that group. So you have to introduce windows. In batch, you don't have to do that, but you can think of it of just having one window that spans everything. If you have this notion in there, then again, this is just a special case of a streaming program with a very large window. And streaming programs need pipeline data exchange always, otherwise you're not staying within your latency. For a batch program, you can also use pipeline data exchange. There's really no fundamental reason why not to do that, unless you have scheduling constraints that, let's say, the producers of data think mappers, and the consumers of data, think reducers, cannot be brought online at the same time, in which case you may want to fall back to a blocking data exchange, which you can think of as a stream that is fully buffered. So the producer can just produce stuff, push it into the stream, and the stream has a buffer that is large enough that it can just push all its data into the stream, go away, and then the consumer comes up and drains this stream. So this is really internally how Flink thinks about these programs. So what does this mean if you run a batch program? It means that, yeah, I mean, you cannot really read any of these texts there, but I hope you can sort of see the data flow graph structure here, which is important. So just to tell you, there are little boxes here, which if you could read them, they would tell some characteristics of the stream that's flowing from here to here, something like, okay, this is just a one-to-one forward stream. This is a stream that is using a hash partitioner to split itself up. This is a stream that is, that is materialized as a pipeline breaker, so produce first, then consume, or it's a stream that is really pipelined. And in a lot of these programs, you can run a lot of them as truly pipeline streams. Interestingly, the operators are often blocking. If you have a sort, you do consume your entire input stream, then sort, and then produce. So the operators are blocking, and you're not running everything at the same time as you would with a lot of streaming programs, but mainly because of the characteristics of the operations running in the operators. And if you have that, it's actually a good thing to exploit this. So if you run this on Flink, if you throw out this program, it's not going to just bring up everything at the same time and try to run it. It's going to start streaming the data, and as soon as streams are available for the successors are brought up, and the predecessors are torn down as their streams are produced and consumed. So the net effect of including this in scheduling is actually that the execution doesn't behave all that different than a batch execution, with the exception that the lifetime of the operators overlays. So if you look at the breakdown of a Flink job, this is from the web front end after it has been executed. It's a pretty short job, actually 1 second or so. It's just an example on toy data, but it gives you an impression. You can see a lot of these things may start at the same time. If you have enough resources, they may run. And even though it says join here, and this says co-group, even though this join produces input to this co-group, the co-group starts very, very soon after the join, because as the join is producing data, the co-group's already consuming it, putting it into its sort buffers, starting to sort the first parts, maybe even attempting to start merges in the background and all of that. It's a bit like when MapReduced introduced that the reducers can come up early while the mappers are still producing things. It's sort of similar like that, but in a more general paradigm. All right. One thing that we learned is really important if you want to do such a thing is managing the operators properly. Because if these operators are up at the same time, there may be parts of this co-group running in the same JVM as this join. And if you don't make these operators behave, they're going to kill each other. They're just going to, one is allocating its data structure, it makes some assumption, the other one makes a similar assumption, and then they're going to eat away each other's memory, and the JVM just, boom, it's away. So one of the really important things that we learned you have to do for this is actually manage memory. And I don't have time to go into this into detail. There's been a recent blog post about that from one of my fellow Flink committers, Fabian. He has written an awesome blog post about this. So whoever's interested, I recommend go to the Flink blog and check it out. Just going to give you the very basics. What Flink does is at startup, it reserves a certain portion of the heap by allocating byte arrays. Think of it as memory segments that a memory manager in your C program owns. And that logically divides the heap into the data structures that the workers need for themselves, the memory that we use for sorting, hashing, caching data, and then some remaining heap space that is for the user code. I think the ratios don't quite match. We leave a little more to the user code than it looks like that on this figure, but this is the conceptual thing. And then all operations place data always in binary forms into the managed memory buffers and try to work on this binary data as much as possible. So they really build their hash tables in binary form. They even sort binary data to a large extent without ever deserializing it into objects by means of this special serialization framework that we built for Flink, and that uses this type information and extraction that runs in the client that I showed you on some very early slide. While you submit the program, you look at the types, you pre-generate the serializers, and you pre-generate utilities and analyze classes to figure out, okay, how do I actually compare data in its binary encoding? For some data types, it's trivial. For others, you have to sort of compose and change encodings for certain situations, and then you can do that. And yeah, the net effect is that even if you run out of memory, so it gives you very robust behavior in memory, but also if memory runs out, you get a very graceful behavior because you can just take bunches of these pages and move them between memory and disk. And yeah, especially this is for the hash join, it behaves pretty gracefully. Okay, let me skip over this a little bit and just give you one last thing before my time runs out. I mentioned earlier on that most systems, if you're running iterative jobs, are actually doing that by submitting multiple programs into the cluster. The same thing again and again, and try and keep intermediate data in memory. What we've built in Flink is a way of having a feedback in the data flow. So you have a function that encapsulates this step that you're repeatedly executing, and rather than deploying it again and again, consuming the previous deployment's data, you deploy it once and you allow it to feedback its results to the beginning. This has the nice characteristic of, first of all, you're only deploying this once. You can actually keep data structures around across iterations. It has, because we surface this in the API, the nice characteristic that the system knows about that. It can figure out for you what is loop invariant and cache that in memory. And yeah, and with all that, we're actually able to get some pretty good results on very heavy algorithms in the machine learning space. So this is a slide. You may have seen this if you went to the talk from Till yesterday. He was talking about machine learning with Flink. This is the matrix factorization use case that we scaled to some, I think, a pretty good scale actually, on not too large hardware. So factorizing a matrix of 28 billion entities means you're dealing with many terabytes of intermediate data sets. Although the input data is only, it's a bit below a terabyte of input data. The algorithm has the notion of blowing up intermediate results vastly and doing complex computations. And the way of having this very well-behaved feedback loop, this very well-behaved memory management, actually allows you to scale this pretty far on a decent, on a not overly large cluster actually. And the next thing that you can actually do if you do closed loop iterations is, and I was hinting at that earlier, is you can keep state across individual invocations of whatever you do inside your iterations. I'm not going to go into details. This concept called delta iterations is a way we try to abstract mutable state in a way that it doesn't break the functional abstraction. The one net effect that you can get of keeping state around, let me only give you that before I wrap it up, is that you can write algorithms such that they work on whatever they need to work on, whatever work needs to be done depending on the changes in the previous step, and you can not look at the, let's say, the already converged parameters that you can exclude because they haven't changed for a while and none of their training points gave you any new insight, so why should they change now? You can write the algorithm to ignore those points and selectively compute what you discover as a new update in a subsequent iteration and just update that into the mutable state. If you go back to that abstraction, which you have in most systems, the result is whatever comes out of the step function. So you have to implicitly carry forward all your results every time, otherwise they're going to be lost. The net effect of keeping state is you can just compute on what needs to change. You have some state that actually holds whatever your result should be, and this is going to be the result of your computation. So with that, you can actually implement a lot of graph algorithms or machine learning algorithms which have this structure of having graphical dependencies between the parameters. In a very efficient way. So this is a slide comparison. if you go from Hadoop to the, let's say, naive way of iterating with Flink, you get all these caching and memory, deployment benefits and so on. And if you then say, okay, let me switch to the Delta model, you can actually, again, shrink this computation. And you can see that especially if you do more iterations, the later the iteration is, the less work it usually does. So if you can get to much lower error rates, but just focusing on the parameters that's still relevant. Adding few iterations doesn't cost all that much in that model. Okay, that was a lot of contents. Thanks for staying with me. I'm going to put up this slide for the end. It's what we're working on right now. Streaming is under heavy development. I think it has some very interesting characteristics right now in the way it allows you to do low latency with states, with user-defined state, without sacrificing the niceties of a proper stream processor. We're working on master failover because in highly available, we don't have this in the system as of yet, but it's pretty crucial for highly available streaming setups. Monitoring integration with other Apache projects, and well, of course, like usual, the library is actually the most active parts. They attract most people because they have a comparatively low barrier of entry if you want to work on something. And if you find this interesting and are excited and want to learn more, we'll actually have a Flink conference called Flink Forward later this year in October here in Berlin, actually in Kulturbrauerei, exactly where Buzzwords was last year. So if you're a frequent Buzzwords guest, you will know this place. It's also a nice location, and we're putting together the program. So if you are playing around with Flink, if you're working with it, if you have prototypes, experiences, suggestions for features and improvements that you want to share, the call for participation is still open. So feel free to also share your ideas and results with us. Thank you.